video.
Okay, we might as well get started here. So we have a good portion of the cabled array team in the room here to help answer questions. So Deb Kelly, which is myself talking, I'm the director. Oris Kauka is a project scientist. Brian Itting is the project manager. Dana Maniling, Skip Denny, and James Tilley are all from the Applied Physics Lab. And Skip is heavily involved in field operations as well as the engineering part of the program. And Dana and James is we'll get into the infrastructure in a minute, but James is one of the leads on the secondary infrastructure, specifically the secondary nodes. And Dana and both Oris have been instrumental in looking at the instrumentation. So just as an agenda, I'll give a very brief overview, pretty brief overview of the cabled architecture, the primary and secondary infrastructure, some of the resources that we have available and that will help you plan add-ons. I want to emphasize that almost all of this information is on the oceanobservatories.org page, and if you have any questions, we can help direct you to the information. Following maybe 15-20 minute overview, I'll hand the ball over to Dana, and she'll go over the most critical part of this first consultation phase, which is to go into more of the details about the secondary infrastructure, the testing, and lessons learned, and then what we can offer the community to help in these efforts. So the cabled array, John Delaney, as many of you know, led the effort. He was basically the success of getting everything installed on time and under budget was thanks to him. The major installation phase for the secondary infrastructure occurred last year during a long field program with the UW ship, the Thompson Ropos. And then this summer, we did the first operation of the maintenance cruise, also using the Thompson and Ropos. These operations maintenance cruises now will go on every year. As they're planned out, they'll typically be about 30 to 35 days with some permutations depending on what happens to the infrastructure the year before and, of course, what proposals are successful with the community. So it includes 900 kilometers of high bandwidth and high power cable, most of you know that run on two main strands from Pacific City, where there's a shore station. There's a backhaul that runs from Pacific City. There's a redundant backhaul to Portland, up to Seattle, where there's another cyberpop, and then all the data flow from there to Rutgers University, who leads the cyber infrastructure part of the program. So the cable infrastructure has been operating for a couple years now without any real issues. It was installed by L3 Meripro. I'll show you that in a second. And then so everything with the black lines that run across from Pacific City out to Axial Seamount, and then down to the south to Slope Basin, inboard to near Newport. That is the primary cable. It was built to telecommunication standards, and then the orange boxes are primary nodes, and I'll show you those in a second, but they're basically the plugins and communication that provide a lot of power and bandwidth on the seafloor and extend to the main work sites through extension cables, and I'll show you that. The Applied Physics Lab built 18 junction boxes that provide the lower power and bandwidth for the instrumentation on the seafloor. These have been installed now for 2 years, and all of them are operating. We haven't had any problems with that at all. We also have two different kinds of moorings, and I'll show you an example of one of those. There's 5 of them on the system. And I'll go over that. But again, all this information for the site localities is on oceanobservatories.org. So there's 5 moorings up to 2,700 meters tall with two different kinds of crawlers. There's about 120 instruments now providing real-time data with two-way communication, so we do have response capabilities. And as Dana will talk about, this was specifically built in mind with a lot of power and bandwidth for communication, or for expansion. So this was a December status. I think it's pretty remarkable for a system that hasn't ever been done before, that we have such high fidelity in terms of operational status. And again, it's to one of the things that Dana will emphasize is that it's really due to the rigorous testing that we go through here at the UW. If you've been on the oceanobservatories.org website, you'll see that all the data now have been streaming, all the instruments have been streaming now for about a year and a half, and those data are passed to Rutgers, and the data are now starting to become available through the Rutgers CI website. All the seismic data is available through IRIS, so they're going to be making the data available as it comes on and as we look at it in more detail, but the updates will be provided on the website. So I don't know if you can see the video, it's kind of clunky on WebEx, but so the primary infrastructure, L3 MeriPro, working with the UW, was a great collaboration. And this is these primary nodes each provide 10 gigabit and up to 8,000 watts power. There's 5 science ports. Dana will go into that in more detail. One of the major considerations in the planning of this program was operations and maintenance and trying to keep the cost down. So we went with wet-mate connectors for a lot of the infrastructure and instruments because it means that they can be plugged in with an ROV. You don't have to bring the platforms up and down through the seawater interface, and it really cuts down on the operational cost. In addition to the 5 ports, we have 2 high bandwidth science ports. One of those at Axial is used, the 10 gigabit port is used for directly connects to an high definition camera, which is now streaming live 8 times a day, and it's on the website, you can access that. And then 2 backbone expansion ports. We have pulse per second timing, and there's 2 different parts to the primary node. One is the part that takes the 10,000 volts and converts it down to 375, and then the other one is the science interface assembly, which again, we designed it this way so for operations and maintenance. The backbone part with the power conversion is directly hardwired to the backbone cable. The science interface assembly can be removed with an ROV if there's any issues with it, and it provides the power and bandwidth to the secondary junction boxes and other platforms. We designed, building off of what the Canadians learned on Ocean Networks Canada, we interfaced with Ropos a lot. They did much of the installation on Ocean Networks Canada. And people that are thinking about deployments will need to interface with us a lot. This summer we'll be using JSON, probably follow-on summers, because it really takes a lot of
planning to ensure success with ROV operations, especially for people who haven't had a lot of practice using ROVs. So Ropos goes 12 on, 12 off. This day, during 21 days at sea, we churned and installed 130 instruments, 13 platforms, the 6 science pods on the profilers, and 2 profiler moorings. It was a very successful cruise, and we hope that that continues through the next summers. So this is I'll go through, kind of walk through this is a secondary infrastructure. So again, this was all built at the Applied Physics Lab, and these are really the power outlets, so to speak, communication outlets at the main experimental sites. So the backbone primary nodes we put in places that were environmentally quite safe, and then, for example, at Axial Seamount up on the edge of the caldera. And then we installed 33,000 meters of extension cables out to the secondary junction boxes, which sit right in the main experimental sites. They are configurable, as Dana will tell you, they are configured for each science experiment, for each individual instrument, so we need to know the power and communication.
And one of the great things about this, we also use wet and dry make connectors depending on the instrumentation. But one of the great things about these secondary nodes is that you can daisy chain them. So there's an expansion port, which means we can add on future secondary junction boxes as necessary to adapt to community needs. And Dana will go over that in more detail. This is an example. They basically lock into the bottom of the ROV, so we can set them, recover and set them down within less than a meter of where we need them. Skip and I work in detail for cruise planning. This typically starts in around January, interfacing with the ship folks. I'll show you a picture of the deck. This is a typical deck layout. Again, because of operations efficiency considerations, ships are expensive in ROVs. We do a ton of detailed planning, and this is one of the deck layouts. Typically, we have, on an O&M cruise, we'll probably have 3 legs leaving from Seattle and going in and out of Newport to accommodate all the infrastructure. And this is this next slide is a kind of a typical. This is the fantail of the Thompson, and you can see that there's almost no walking space. This was a cruise dedicated to turning the shallow profiler components and some of the secondary junction boxes. So again, it takes a lot of close communication to ensure that this is successful and that we can get everything on board. For those of you who've been involved in the program, there's a few main study sites. I'm going to show you just a cartoon of the coastal cabled and endurance array. We share the infrastructure that runs from about 80 meters off Newport, Oregon, down west to 2,900 meters, which is the base of the subduction zone at Slope Base. And for those of you who haven't been involved in the program from the beginning, NSF put out a call. It was called Request for Assistance, and there was on order 275, 300 scientists that wrote 16 proposals focused on the cabled array. From there, we spent about a year refining, basically understanding that we couldn't have, 50 primary nodes. We compiled all the science needs that the community had expressed and tried to pick sites where there was the most bang for the buck, and that's what determined the location of the primary and secondary infrastructure that's shown here. So the idea is that we were trying to meet a lot of science objectives for a lot of the community. So the cabled array off of Newport, the southern splay there, addresses everything from looking at Cascadia subduction zone earthquakes to when the currents come upshore and up off from the base of the subduction zone onto the coast there. So we have moorings at Slope Base. There's a site at the subduction zone, at the Hydrate Ridge site, which is a methane seep site that's been very well studied by the community. And there's a variety of science objectives that you can look at, and a lot of the main reports, if you go on the Ocean Observatory's org page, those main reports in the planning and what's out there are all accessible. So this is one of the cartoons that we have, and it always impresses me when I see this. So this is running from the Oregon shelf site at 80 meters as part of the endurance array down to the base of the subduction zone, and what you see is the cabled array infrastructure as well as the uncabled infrastructure, and this is operated by Oregon State University. So there's a variety of uncabled moorings that are complementary to the cabled moorings, as well as gliders that provide three-dimensional environmental measurements from the Oregon shelf clear down to Slope Base, and then they run up to Grace Harbor. So if we look at we've done a lot in the planning. We've done a lot of site survey work at detailed resolution, say 5 meter or less bathymetry resolution for the maps. These are all available to the community. And what I'll show you is 2 of them for Slope Base and the Oregon Offshore. site at 600 meters. So every year we go out there with the ROV. This is all in GIS, so if people need these layers, they can have them. This shows the endurance site at 585 meters and its slope base. And what you see are the lines with all the lines are the cables, so we survey them in detail with the ROV every time we move them or install them, as well as the location of, say, the anchors for the moorings and all the instrumentation on the seafloor. And you can keep zooming into these to show specific instruments. So these will be pretty critical in your planning for looking at the detailed information for locations, depths for all the instruments, as well as cable lengths. And these tie into other information on the website. We also have a variety, these are online. If you go to on the website for the observatory sites, we also have these more three-dimensional diagrams that show you all the instruments and, again, give you kind of a 3D sense of where the infrastructure is, the name of the instruments, the cable lengths, the names of the junction boxes. So, example, PN1A stands for the primary node 1A, and I don't know why it says slope-based PN1C, but that's a mistake. Anyway, from PN1A, and then there's a cable to the south that runs down to MJO1A, which are, again, the secondary junction boxes. And we can, when we do the consultations, we can walk through these in detail with you. We also, if you haven't looked at these, we use them almost every day. They're the functional block diagrams. This is impossible for you to read, but what they do is they provide you a site. This is from slope base to southern high grade ridge, and it provides you every single kind of connector, every junction box, every instrument, all the cable lengths, all the cable types in detail, and it's a great way to get kind of a sense of what's out there and how everything's connected to each other. It also gives you information about open ports. If we zoom into slope base here, so this is a detail of a functional block diagram, and what you see are the four instruments at the medium power junction box, MJO1A, and then the little boxes with H, E, and D are the types of either wet mate or dry mate connectors. And for this one, we are working through the kind of operational maintenance cycles, so we color-coded things depending on how often they would be turned. So I would really recommend that folks that are interested in adding on or want to find out more about the infrastructure, this is a great resource for you. And if you can't find it, we can certainly help you on the website. We can certainly help guide you to this information. It also shows you that where it says in between, like the connectors, if you go from the medium power J box to the pressure sensor to the right there, it has the electrical wet mate connectors, and then in between that, every single cable has the length as well as an indicator for the type of cable that's required there. This is one of our pride and joys for the cable array. These are state-of-the-art moorings. There's really nothing like it out there right now. That was built by the Applied Physics Lab. It's a two-legged mooring that's, again, connected to the internet, so we have two-way communication. We can change the sampling scheme as people put in proposals to augment the sampling scheme. It has a 12-foot across platform. It's kind of a big beast, 7-ton platform that is at 200 meters water depth, and then it has two science pods. One is a winch profiler with an optical slip ring. It makes 9 profiles a day. I'll show you that. It has a variety of sensors on it. And then we have another stationary platform, which is shown in the upper left on the right side of the platform there, that has other variety of instruments, things like ADCP, water column instrumentation, and cameras on it. And the image to the right there shows one of the winch profilers going up and down through the water column. You can see the winch down at the bottom. So we have 3 of these. They've been out there, all 3 have been out there from this year, and we had a set of them out there last year as well. All 3 are operating flawlessly right now, and they're very smart instruments. So for example, the shallow profiler Eric McRae has built into the program that it goes near the surface but doesn't actually pierce the waves. The one out at Axial last week was picking up 15-meter waves, so it's a nice weather station. And part of the driver for that is as the weather gets worse and worse and the waves get larger, this package is smart, so it stays down beneath the main wave action. So these data will be coming online very shortly, but they're phenomenal platforms, and we're really proud that all of them are working right now. So there's 3 of these. You can see the circles at 3A, 1A, and 1C. This is, again, the functional block diagram for in this case, the stationary platform, and it gives you an idea of the sensors on there. So 5-beam ADCP, 2 different kinds of ADCPs, optical backscatter, fluorescent, CTD, oxygen, pH. And again, these were designed with a 25-year period in mind so that there is power and communication, bandwidth expansion capabilities, so we can add on instrumentation to these platforms as required. I won't talk about it, but the companion moorings are the deep water profilers. There's one shown just to the left of the 200-meter platform. Again, all this infrastructure is cabled. It has a modified McLean water sampler on it with a complementary set of instruments. And it goes down. There's a modem at the bottom of it, ICL, that we can power up the profiler with, download data. There's also data stored online within the instruments, and then it goes up and down through the water column. And there's a detailed sampling documentation for the sampling scheme that is also available on oceanobservatories.org. So this is what one of this is Dana and Oris working on the back of the fantail to give you a sense of scale of the science pod. They currently make 9 trips a day with steps to posit specific depth intervals. So for example, if you're interested in pH or CO2, it goes up a certain number of meters.
Hi, Bill. I am actually on the web conference for the OOI. No, but that's okay.
Hey, Marta, welcome.
Yes, it's the cable OOI
Marta,
web.
You're live. Great. Okay, so it makes it'll stop at a specific depth interval and make specific measurements. So one of the key reasons for this is to respond to environmental events such as response to thin layers or storms or megaplumes. And it's great for looking at gradients in detail. And I should say those get turned every single year. The other side I'll just show you again in detail, a little bit in detail, is the axial seamount, which is currently the most advanced volcanic observatory in the world's oceans. The reason that axial was picked is it's the most magmatically active volcano off our coast. It erupted in 1998, April 2011, again this year in 2015, with over 400-foot thick lava flow. So this is again the infrastructure. You see primary node 3B over to the right there, and then all these green cables are the extension cables with secondary junction boxes. There's 2 main hydrothermal sites, and then there's 3 sites for geophysical instruments to look at the seismic activity at the volcano here. And I should say, so we got our first lessons on how phenomenal the system can be for the community. Shortly after the workshop in April, William Wilcock was using the data from IRIS, picked up 8,000 earthquakes in a day, and Bill Chadwick's, these are all core instruments on the cable array. Bill Chadwick was looking at the seafloor bottom pressure tilt instruments, which measure inflation and deflation, and over that same time period, the seafloor fell about 7 feet. We had a large number of the geophysical community looking at those data, and they worked up the data and were actually instrumental in picking where the eruption site was. And then the follow-on cruise that we were out on 3 months later was able to map that flow in detail. So it was really nice to see a large amount of community involvement in that, and I think shades of things to come. I'll stop here after this, but the other kind of data that we do have available is at every single site we go out and image the site with video and digital still imagery before and after the installation. So users that are interested in, one, just seeing where everything is and what the site looks like has those data available, but also it's valuable in planning. This is one of the main hydrothermal sites called El Gordo at the summit of axial seamount. And what you see on the right there is a mooring that takes water samples as well as microbial DNA samples, the digital still camera, a mass spectrometer, and then off in the distance there to the left is the junction box there. We also have, at some of the sites, we have detailed photomosaics. So, for example, at Southern Hydrate Ridge, we've photomosaic the entire seep site, and we've placed the instrumentation on top of those photomosaics. So, again, this is a great planning resource for folks. So I think I'll stop there and hand the, we can open, well, I guess we'll save questions to the very end, but I'll hand it over to Dana.
We'll do take us a minute to switch presenters here, so if anyone has questions in the meantime, feel free to type them into the chat. Okay, so we'll move on. My name is Dana Manelang, and I'm an engineer at the Applied Physics Lab. Let's see. And so I'm going to go over the instrument interfaces. So we're going to kind of zoom down in. Deb gave you a good overview of the whole system. And we're going to zoom in mostly to taking a look at those secondary nodes, because that's where the instrumentation is really plugs into the system. As Deb mentioned, there are ports on those primary nodes and higher voltage, higher bandwidth. If anyone has interest in those, that's something that can probably talk about offline, but for today we're going to focus on those instrument ports on the Seafloor junction boxes. So I'll give you an overview of kind of how the secondary nodes work, the interfaces, some details on those interfaces, all the signals that go into and out of them, and then we'll kind of switch gears a little bit and talk about the instrumentation testing and how we've done integration with the over 30 types of instruments that we already have on the cable. Go through some lessons learned as a result of that, and we'll go through a little bit the facilities and support that we can provide from here at University of Washington. So key architecture points of the cabled array is that each, so this is a network. There's a great piece of hardware out there, but at its core it is a network, and each instrument port has a unique IP address that then you can connect to from shore. We also have power control from shore, so everything we can do basically on a bench top we can do here. Our goal in developing this system was, to give users, so if you have an instrument, the way it looks when you interact with it on your bench or locally, it'll look exactly the same when it's deployed offshore. So we can control power to each of the ports. Timing is all based on GPS clocks. So even out at the most remote instrument ports, we've got 10 microsecond scale accuracy. And then I think Deb talked a little bit about the ROV wet mate connectors, which allow us to pull pieces of the infrastructure out for maintenance and also to add, easily and flexibly add new equipment. So this is kind of a deeper dive into the architecture. In the center of your screen, you see a primary node, and we talked about each of those science ports. So those science ports have an out-of-band line. That's a fiber that runs to the medium power junction box. And you see this is a plus and minus 187, so 375 volt DC power line and a 1 gig Ethernet. And so you can see all of this originates from the shore station, which is in Pacific City, Oregon, where we have, this is where our GPS computers are located. And so we have a precision time protocol in place on the system, which gives us high accuracy timing at all these ports. We talked a little bit before about the high bandwidth science ports. Again, so right now that's supporting systems like the HD camera in full lossless data. So zooming down into the medium power junction box, each MPJ box supports up to 8 instruments, and each one of those instrument ports can be configured 12, 24, 48 volts DC, up to 200 watts. We'll talk a little bit more about the power per port in a little bit, and then those instrument ports are Ethernet, are again configurable Ethernet serial. So once again, the secondary node, or you get down into those, are also called the junction boxes. They're the interface between the array and the instrument. So the in between the primary nodes and the instrumentation on the system. We do configure each of those instrument ports when these systems are built. So the voltage output, the power level, we have both 50 and 200 watt ports. The communication type, also the connector type, and so we'll get a little bit more into that in the next couple slides. So there's 2 kinds of connectors that we tend to use. One is a wet mate or an ROV mated connector, and that will allow an instrument to be placed and connected to that junction box by an ROV. In some cases, it makes more sense to use a dry mate connector where an instrument is actually coupled to that junction box, and it stays on the junction box. And so in that case, the instrument the instrument will come up and down with the junction box, and can't be pulled out separately. So one thing to consider is with the cables in the water, the longer the cables, the less power and bandwidth there is available. There is some drop. We're really not close to those limits in most places in the system right now, except potentially at the top of those tallest moorings. We do get some voltage drop there, but again, there's still open instrument ports. So that's something that, as we look at each individual case, we can determine, whether there's power to support it, and that pretty much bandwidth everywhere. So this is a secondary node being tested in the lab. There's Mike Harrington, one of our lead engineers on the project. So you can see on the end of this is the end cap that you actually see once the node is all buttoned up. And so these are some dry mated connectors. Down here, there's actually some fiber connectors coming in. Deployable by an ROV, so that's the secondary node in its frame, and you can see there's some cable here coiled on the horns on the side of the frame. And you can get a feel for the connector ports down here as well. And then once it's all on the floor, it tends to, on the seafloor, it looks something like this. So you can see the cables coming in from different instruments from the primary node. Here's the connector panel. There's actually connector panels on both ends. One side is for instruments, one side is for incoming, and then expansion ports. So we do have to keep pretty good track of the cables, as you can see from this picture. Kind of illustrates that as one of the things that we track as we put these things in the water is which cables lay on top of other cables. So communication interface, for each of the instrument ports, it can be configured to one of the following: the 10-100 megabits per second Ethernet. That's just a standard 4-wire Ethernet protocol. RS-232, and we do have RTS and CTS lines available on those. RS-45 in either full or half duplex, and RS-422. And some of these we do encourage extra testing just to verify just to verify that the communication works. One of the things that the interface communication also drives is the length of the cable that can be supported. So for instance, the RS-45 and 422 are differential signals. We can run longer cables with those types of communications. RS-232 is typically a short cable, so in the order of 10 meters, and then Ethernet can get about 50, maybe 70 meters out of that. And we have had some success with RS-422 over kilometer-long cables. So the power options on each of those ports, 48, 24, 12 volts DC. Again, this is configured in the node prior to deployment. And power on those ports 50 or 200 watts. So this makes mention of a low power junction box. We actually do have kind of two flavors of junction boxes. If you go in and start looking at the functional block diagrams, you might see an MPJB or an LPJB, and those are medium power and low power junction boxes. They're essentially the same thing other than there's slightly less power available at the low power junction box. And so those max out at 50 watts per port. So for timing, one of the critical pieces of the system is to be able to compare data across a large distance. So we need to make sure that we have accurate real-time timestamps on every piece of data that comes into the system. And so at each secondary node, there's a GPS time base that derives from the shore station. So we can serve NTP. We can support NTP for Ethernet style instruments, or precision time protocol is what the PTP stands for, which is a little bit higher accuracy than the NTP. For serial instrumentation, or for Ethernet too, we provide a pulse per second signal on any of the instrument ports for instruments that need those, and that tends to run about 10 microsecond accuracy. So again, very accurate. And then for serial instruments, a lot of the commercial instruments out there are not used to having these types of timestamps available, and so we're able to timestamp the data as it comes into the secondary nodes. So we have in the instrument port as a serial data comes into the instrument port. It gets converted to a TCP/IP protocol. As that happens, it's given a timestamp. So if there's minimal latency between the measurement taken and when that data is output from the instrument, then it'll get an accurate timestamp at the junction box. And again, that's for serial instruments. Here's another closer view of those connector options. So here we have the ROV wet mates, and those are ODI Nautilus 12-way connectors. And so here's a close-up of what one of those connector panels on a node looks like. And so as you can see, there's there's one here. This is probably the most full one that we have out there, but we do have a spare port here. And then for a dry mate, we use Impulse MHDXL 12-pin bulkhead connectors. And so anything that connects by dry mate, again, connects directly to the junction box. And so anything connected to that cable has to travel with the junction box. And so as we work to bring new instruments on, one of the things we'll do is evaluate, how long an instrument needs to spend in the water, and what its maintenance cycles are versus the rest of the node to determine whether it should always travel with the node or whether it can whether it needs to have an ROV wet mate. Obviously, there's more cost associated with the ROV mates. So I think we'll be making these presentations available, hopefully through the website. But this is a close-up or a detailed look at all of the MHDXL pinouts, and so these are basically configurations for a 12-pin, that dry mate pinout. So this is the instrument connectors here, right at the end of the junction box. So configured for different communication protocols. And so again, this gets configured before the junction box goes in the water. We would work to figure out which communication protocol and which other signals. So you see here, I can go through a line of this just to interpret some of the alphabet here. So we have a power ground, a pulse per second. So this is a pulse per second plus down here. On pin 11, we have a pulse per second minus, so that's a differential signal. On pin 3, data ground. Pin 4, a TX, and pin 5, RX. And again, these vary depending on the communication protocol. Pin 6 and 7 here is actually a time of day string, so for an instrument that actually needs to get a NEMA-style time of day string, that's an available option. Although for most Ethernet instruments, what we've seen is that the combination of using the 1 PPS and an NTP server tends to be the way that most people like to keep accurate timing. And then we've got more RxTX, pin 10, so if it's a 24 or 48 volt instrument, one of those will be populated here on pin 10. So again, that's predetermined prior to when the node's configured, the pulse per second minus, and then pin 12, if it is a 12 volt instrument, then that's on pin 12. And the reason for the power being separated is just so we, so that we can't plug in 48 volts to a 12 volt instrument. Oops. There we go. We talked a little bit before about how the communication protocols will drive the cable lengths. Again, these are rules of thumb. So for RS-232, we tend to not go longer than about 10 meter cable lengths. For the differential signals, 422 and 485, we would recommend not going longer than 500 meters for a high data rate, so at kind of the 200 kilobits per second range, although we are successfully operating cables in excess of 1,200 meters at 38.4. And so that does scale. So those same instruments, we've tried them over those same cables in the lab, and they do not work at the higher data rates. So Ethernet, again, 70 meters. Recommend trying to stick below 70, maybe 50, maybe conservative. So for 10100. So this is a little bit of an eye chart, and we're switching gears a little bit here as we start talking about how an instrument might get integrated into the system. So we've split it into kind of 3 phases here, and I apologize that these letters are coming out a little bit small. I'll talk through it. So the first phase would be kind of the scoping and proposal process, and so here at UW, we're willing to work with and meet with teams who are interested in putting instruments on the cable and help to plan that process. So we've put together a planning form. I'm not sure if those have gone out at this point in time, but that goes through kind of all aspects of the system that would enable us to understand how it would connect to the cable, and then it would also could drive into the instrument development process. If it's a commercial instrument, it might be a little more straightforward. If it's an instrument that's being developed specifically or that's being converted from a battery-powered system to a cabled system, that would be a good good time to go over some of those details before actually making some of those design decisions. So once a instrument is approved, ready to go on the cable, there's a build process, and then and note that we've actually we recognize the fact that some of these things might take some iterations, and so in the planning process, certainly could work with teams to revise and kind of make all of those right design decisions to get an instrument that works the best with the cabled system. Once we're ready to build and integrate, once a prototype system is available, then there'd be some testing and integration with our junction boxes, and I'll show you a little bit more about some of the test systems that we have that we can make available for that type of testing, and so that may drive, again, this recognize that it's an iterative process, and that could drive some modifications that would then continue on through the build process until we've successfully gotten through and integrating that instrument with the secondary infrastructure. And at that point, one thing to always consider in this entire process is how the deployment and operation and even the recovery of the instrument would work out. So before it goes in the water, we want to know how that's going to happen, how it's going to be operated, and how it gets eventually recovered. And then there'd be a deployment, and then we'd move into an operations phase. So we'll look a little closer at that instrument testing, and we've had over 30 types of instruments that we've already connected to the cable array. So I'm going to say that I think almost any instrument can be connected to the cabled array, but we need to test it, and we need to make sure that the interfaces are working. And so the objectives of the test program that we've put in place so far is to verify that the instrument is complete, that it's robust enough to survive deployment, to operate, and to function on the cable. What that does not include is checking the calibration of instruments. We don't presume to know the measurements better than the people who are developing the instruments that do the measurements. We just want to make sure that they work up to their capacity. So the second point is that we want to make sure that the instrument can function as an integrated part of the array. So what that means is that the interfaces with the cabled infrastructure are correct, and that it won't either be susceptible to interference. Again, maybe an example, an instrument that's being converted from a battery-powered instrument to a cable-powered instrument might be used to a cleaner power supply off of that battery. We try our best to give clean power, but it's never going to be a battery. And so things like that, you just need to work out. And also want to make sure that any new instrumentation does not cause interference or cause drive corrosion or anything like that for cabled systems that are already in the water. And again, as a result of this level of testing, we've had success across the board. Here's the table seems to have gotten bigger. Here's a list of instruments that we've already connected to the cable and have all functioned on the cable. Again, these are all the core instruments for the system. And so the test flow that we follow on instruments, and again, these have been performed on every type of instrument that we've put on the cable so far. Start with a physical inspection. It seems obvious, but you'd be surprised how much stuff we've found things like misassembled connectors, and even on commercial systems. I mean, a lot of the instruments that we've evaluated so far have been right from instrument vendors, and they don't always pass the sniff test. We've seen loose screws, things like that. So we look for things like that, and we understand things can happen, especially if instrumentation is shipped back and forth. And so after that, just a basic power on test. Does the thing work? Can we power it on and talk to it the way it's supposed to talk to us? We do 100% pressure test on all pressure vessels that are on the system. That's self-explanatory. And actually, one thing I will say about the pressure test is we do pressure test slightly above the pressure where it's going to be deployed. So our spec for the instruments on the 200-meter mooring, for instance, is 300 meters. And the reason is there's a factor of safety there if we do that, and also we're able to, those two-legged moorings have some air in it, so it's possible that those could get put in at 205 meters, and so we want to make sure that we've accounted for a little bit of overage there. I definitely would recommend a design pressure of much larger factor of safety. After that, we do some electrical characterization, and that's really understanding what kind of inrushes, what kind of current draw, what the power consumption of that instrument looks like, and that's just to make sure that the power that we're providing on our on that instrument port will be able to handle the load that the instrument takes. And so this is a key one here, is electrical isolation, and so the reason for this is one, to make sure we're not causing corrosion on the system by setting up electrical currents in the water, and so especially for a metal housing, we want to make sure that we're not seeing stray currents in the water. And that can also mess up a lot of sensitive measurements. And so our spec has been that we test to 10 megohms at 50 volts on all pins. And actually, we'll get to lessons learned, but just a few anecdotes. I mean, we have found that not only can this uncover design issues, but it can also uncover build issues. Again, commercial vendors where a wire seems to have gotten pinched somewhere in the housing and inadvertently is shorting the power pin to seawater. Those are things that we want to avoid, and those are the types of things that we've found in doing this test. For brand new systems, we recommend doing a burn-in. Our standard is 200 hours, depending on the system. That might change, and that's just to catch any premature failures in electrical systems. We all know that sometimes things don't quite meet the spec that they're given, and so that burn-in allows us to make sure that something's going to work for the long haul. And then after doing all of that, after subjecting an instrument to all of that, we go back and we run through the full functionality that we expect to see out of it when it is deployed. Make sure everything's still working. Once that's all done, then we go and we plug it into our secondary node. And so through doing that kind of testing, we've learned a lot. And here's just a few things that I think are very important to consider. First off is material selection is very important. You can see on this housing, this is an anodized aluminum housing. It didn't have any zincs on it. So after a 1-year deployment, we actually had major pitting here in the aluminum itself. It could not have endured much longer without flooding that housing. So secondly is always test for electrical isolation. As I mentioned before, sometimes it uncovers some design issues, and sometimes it uncovers just some assembly issues. We don't want to short things to seawater. Third thing is design all the systems with deployment and recovery in mind. So if an ROV is going to have to put this thing in the water, we should put the pickup points on the on the instrumentation on the frame that an ROV would be able to use. So make sure that there's a path for getting it in the water and recovering it. Next is double-checking connector pinouts. It seems like an obvious thing, but one of the practices we've adopted is whenever we have kind of a new test scenario, is we always check for where the voltage is and verify that it's on the right pins before we plug an instrument into it. And then the second thing is that I don't know how many times we see things like TX and RX reverse, so transmits and receives, to make sure we know which way those are going. I think we did send back a few instruments to get that fixed. Again, not always the custom instrument. Sometimes it's commercial stuff, so it's always good to check. The next one is that we do need to understand the electrical transients and sensitivity to noise. So here's a plot. Actually, I think this is from an ADCP. So again, it's an instrument that often is operated with a battery when it's operated with an external power supply. It does take a fairly large initial inrush of current, and so we can handle that. There are things we can do electrically on our system to become more robust to those large inrushes, and so that's part of integrating with our secondary nodes is just understanding that. And sometimes that doesn't come at the start of a at a turn on. It may be during a sleep-wake cycle or during sampling. For things like our cameras, it's not until the lights are turned on that we see some of the big current spikes. And then the next thing is allow for cable lengths, so that if there's a longer cable length over a 50 meter, there could be a voltage drop, and so maybe it's best to design for the higher voltage or a larger voltage input voltage range. Same thing, communication signals is make sure that the appropriate communication signal is being used when we know what the cable length needs to be. And then a couple sort of software type suggestions is one is that the menu-driven user interfaces are a lot more difficult to program to. So we have to think about these instruments being controlled by a computer, not necessarily a human for the long term. So to make an interface that a computer can easily interface to. And then lastly is avoid at all costs getting into recoverable states through software. We found inadvertently that one particular instrument, there was a very bizarre set of characters that when it saw that, it basically went into a brick state and needed new software put on it that could only be done on the bench, and so luckily we discovered this before we deployed it. We're able to address the issue, but it's things like that. If we've seen examples of instruments that have been designed so that if you want to recover from an error state, you need to disconnect some internal battery, and that's really hard to do when it's deployed on the cable. Actually, quite impossible. So we want to make sure just that the states of the instrument are robust. So where we do most of our testing and the facilities that we have for this here, again, that can potentially be made available are a chilled saltwater tank. It runs at about 4 degrees C with an Agilent power supply, power analyzer. We use a Fluke 1507 insulation resistance tester, and we also have a chest freezer that we use actually mostly for secondary nodes testing, but want to make sure things work when they're cold. Also, on site at UW in our Ocean Sciences building, there's a saltwater test tank, a large tank. So for things that don't fit, we do have a few instruments that we've integrated that are just a little too big for our, our 2x4 foot saltwater tank, and so those get tested in a room temperature saltwater tank that's 24 feet by 10 feet by 13 feet. And there's also a fairly good-sized pressure test vessel, 24-inch diameter, and 8 feet long. It can accommodate quite large systems, and so that's available here as well. It's where we pressure test all of our secondary nodes before they're deployed. So we talked about testing against secondary nodes. There is some portable test equipment that we can use for this. We have portable secondary node simulators, so that basically is the guts of a secondary node in a rack mount system. So it's got an output port, and those output ports can be configured just like any of the secondary node ports. Similarly, just a much smaller system, but it's kind of a small hand-carryable portable instrument port, and so that can output 24, 48, or 12 volts. It can handle the different kinds of communication protocols. It uses the same serial conversion cards that are used in the actual nodes, and so testing communication protocols to our portable instrument port is a good way to go. Capability out here at UW, mechanical engineering, pressure housing designs for frames, mounting systems. We've done a lot of that for this program in particular. Electrical engineering, everything from board design to testing, component selection, integration, firmware and software development, and then you saw the pressure and the saltwater tanks and those photos, and also we have a clean room that we use for final assembly of all of our nodes, and so that system can be made available. I think so that's the end of what I have. Do we have some questions that we want to? I'm going to turn it back over to Deb now.
So if people have been, as questions come in, we've been trying to answer them online in the chat. There was one question that came in about, that we didn't talk about yet. In the scoping and cost considerations for the cable array, where it is expandable. There's a mid-plate site that runs between Pacific City and Axial Seamount. There's another primary junction box. And in consideration of the OOI costing, at the time it was decided that it would be instrumented with, it contains the backbone interface assembly, which is one of the functions is to convert the high power down to 375 volts. The second part is that I mentioned earlier was the science interface assembly, which is what it's a removable, reinstallable component that goes in the primary node, and it's wet mated. We can pick it up with an ROV. We've done it before, and reinstall it. That site also, NSF recognized that it was a site that the community had wanted for expansion. So there is also a 5-kilometer stub of primary backbone cable that runs from the primary node towards the Grays Harbor site. And so the thought was that with that 5 kilometers, we can pick it up above the water put on another cable, primary cable, and expand it out that way. And we've done that with the drill ship before, so that's all tried and true. They're in looking forward to community experiments at the mid-plate site. Certainly that will take some discussion with NSF and have it, community-driven. So we do have a spare science interface assembly that could be put into the primary node there. It is a operations and maintenance spare, so there would have to be dialogue with NSF about building another SIA for that. So that then would act as a spare. So that's a longer-term dialogue, but certainly we have heard that there's different agencies and people that are interested now in looking at the mid-plate site for expansion. So it'll be a follow-on conversation, I think. So there's a question about, for those of you who been involved in observatories, there's a question about, MBARI had developed a communication device called a puck. Early in the days of, there was a lot of discussion. There was an 80-member team called a STAC, which was Science Technical Advisory Committee. It included scientists, engineers, and CI folks. It was led by Doug Luther at Hawaii, and we really formed, that's what came up with the design and the final design network for the Hawaii Observatory as a whole. During those early days, there was interaction with MBARI about using pucks, and for a variety of reasons that did not go forward, but I think in the future, as more observatories come online, that's something we can talk about.
And I'll add too, something about this infrastructure is that the infrastructure provides this pipeline that the interface is really different than it would be so the only that is what we on the shore side is we're always connecting to a TCP/IP port rather than a COM port like a serial instrument might connect to a laptop on a COM. They always use an Ethernet space.
We're going to repeat part of that because somebody's mic is open. We're going to mute him in just a sec here. Okay. Go ahead, Dana.
Sorry. Yeah, I don't know how much of that you got, but again, the infrastructure is really designed so that the connection to that particular piece of equipment or instrument looks just like it does if you're connected to it on your desktop, with the exception that what you're always connected to it through an IP address or an IP port. So if it's a serial instrument, it gets converted into a TCP/IP protocol, but all the commands remain the same.
So there's a question that came in about, so ONC, they were in the water before us, and they have a number of working groups that collaborate virtually. We've had some, during the early testing phases of the program with respect to data, there have been some workshops where, say, for the coastal community would come with subject matter experts and look at, say, individual instruments. And certainly there's going to be follow-on workshops for the OOI that are more specific. And I believe that part of that will evolve into specific working groups, whether it's for example, lessons learned for ADCPs, certain kinds of instruments, and also for site-specific working groups. I know for example, there's a Gordon conference this spring, or this in February that NSF is in part funded, and there will be a breakout meeting specifically for folks interested in adding infrastructure onto Southern Hydrate Ridge. So they will, I assume they will definitely involve. In terms of the science components, so there's an oversight committee called the OOSC, Ocean Observatories Scientific Committee, and then there's also, which is made out from people outside of OOI, and it's run through UNOLS. And then there's another committee internal to OOI called the Science Oversight Committee that is comprised of project scientists. And so I think as we move forward, definitely we will have more and more working groups on specific topics. But what I would encourage you to do is if you have specific topics that you want to develop a working group, send Ocean Leadership an email. You can go online on the oceanobservatories.org. There's a help desk, and all the feedback we get from the community, more is better. So, thanks.
A couple more questions coming in. One about the point person for the data portal. Is there anyone online who can? We tailor this presentation to the electrical and mechanical interfaces. Is there anyone online who can address the?
Currently, the way that the data, if there's somebody on CI that wants to jump in, that'd be great, or Ocean Leadership. Or NSF, but currently what happens is if you put in a help request to the oceanobservatories.org, that the cyber infrastructure folks see that, and they focus a specific request to either someone within, depending on the nature of the request, either someone within the cyber infrastructure group, the data management people, or if in some types it may. The help desk is what you'll set up for. They funnel it either through someone to the data management group within CI at Rutgers, or there's often cross-project team members, so science, engineering, and the scientists within the program that will work with the CI team to work things out. So that's the help desk is certainly the place to start.
And a quick response on the gliders. Actually, I saw John Fram on the system. So there are no recharging docks for gliders. We love the idea of kind of resident vehicles and recharging on the cable, and that's certainly the kind of technology that this is built to drive. It's not a part of it right now. So yeah, hopefully you see some proposals about stuff like that.
Yeah, and there was in Boston last week, there was a UNOS meeting called Descend 2, which was to look at technology, everything from platforms to robotic vehicles, ROVs, AUVs, looking forward to the future. And there was a lot of discussion about, there's been significant progress in optical and acoustic modems to, for example, expand the cabled array for folks that didn't necessarily need to use a cable but wanted bandwidth and communication. So there's other opportunities there. There's a question about when proposing a new instrument, do funding requests go to a particular part of NSF? I think it depends on what, if it's a new development instrument, it would probably go to OTEC, or if it's an instrument that, say, is already tried and true. I know NSF has funded some instruments already in planning for their future use on the cable. And in that case, I think it may follow a different path. I don't know if Jean is still on, but she could answer that. I did notice in the notes there was a question about adding instrumentation, and if you go under the oceanobservatories.org and look at researchers, there's a whole section. NSF is certainly encouraging people to put in proposals both for data as well as adding on to the observatory. And there is initial information for people that want to propose instrumentation. So we will definitely PDF these slides and post them on the website, so they'll be available for everybody. Any other questions? So this is the first quarterly webinar. So they will be every quarter, duh. And you know, there's some lessons learned for us on this end. I think for us it's been a good experience. There are, if you look on the web, there's still, if you want a one-on-one opportunity to talk with us, we have, those are still available for sign up. And again, they'll be every quarter. So anything we can do, it's a facility, and we're certainly here to help you. So anything we can do to answer any questions, or you know, whatever we can do. Again, the help desk is a really good place to start, but we'll do what we can to help you out too. Okay, if there's no other questions, I think we'll wrap it up. I should say there was another question about whether funding has to come through NSF. NSF will certainly be the main contact in terms of adding on instrumentation. We'll have to go through them. But if you look at the information on the website about writing proposals, it doesn't say specifically NSF. So there's certainly opportunity for other countries, industry, whatever, to add on to the Cabled Observatory. So it's not, you'll specifically see it's not NSF specific for funding.
Thanks for everyone for logging in today. Hope you guys have a great day, and we'll be hearing from a lot of you soon. Okay. Thank you.
Yeah, we'll also make the recording available. We're not, since it's the first time we're done it, we're not sure how it's going to work, but it'll certainly be up there. So, and we'll also mail out the information forms for folks interested in adding infrastructure on. So.
Thanks, Jen. Thanks, Brian. Thanks, Horst. Thanks, Dina. And Mike Harrington, if you're there too. I thought you did great.
Thanks, Jean. Have a nice day.